Hello everyone, this is Mr. Froelich. Today's screencast will be going through the global wind belts. Now, in order to go through the global wind belts, we first need to review a couple basics about wind from the day before. Now remember that wind only happens because Earth's surface is unevenly heated by the sun. This means that sunlight hits the Earth at different angles depending on your latitude, north or south, or distance from the equator. When this happens, it takes that same amount of light and it spreads it out over larger or smaller areas, which will then either make it warm up or cool off. So at the poles, that air is spread out over larger areas, which makes it feel colder. When these temperature changes happen, it also creates differences in pressure, and as a result, the air will move in a convection current trying to equalize that pressure, and that movement of air is basically wind. Now, yesterday we discussed how convection currents can cause wind, and today what we're going to do is learn about the patterns of wind across the entire planet and their effects on climate. So one of the things that we are going to cover today is setting up all of the patterns for global convection currents across the planet. Now, in order to do this, we need to highlight a few key latitudes. So we'll have the equator, 30 degrees north and south, 60 degrees north and south, and the North and South Pole. Now, the reason that these particular latitudes are chosen will become clear in a little bit. So as we begin here, I want you to remember that air at the equator is receiving the most direct sunlight, which means it's going to warm up the most, and we all know warm air rises. Now, this air is unfortunately going to cool off and sink before it reaches the North Pole. So the picture I showed yesterday in the screencast was not exactly accurate because it showed convection cells going from the equator all the way to the North Pole, where instead that air cools and sinks around 30 degrees north and 30 degrees south. When that air sinks and hits the ground, the orange arrows represent how it spreads out across the surface, similar to when you spill a glass of water and that water hits the floor and sort of splashes out in all directions. So besides the air rising at the equator, we also have cold air sinking at the North and South Pole. Remember, the North and South Pole receive very little solar energy because of their angle, and in turn will be colder. So that cold air sinks, and the orange arrow again represents that air moving across the surface. Well, now I have an area where the two orange arrows are meeting at about 60 degrees north and 60 degrees south. This, in turn, causes rising air because the two orange arrows hit and have nowhere else to go. As a result, I've now completed my other set of convection cells. For simplicity, I've only drawn them on the left side up until this point, but I want you to realize that they actually do form on the other side in a symmetrical fashion, which means they happen the same way. These also are not two-dimensional convection cells like we've drawn so far. These are actually three-dimensional rings that will connect across the planet. So the ones from the left side will connect up with the ones on the right side. Each of these convection cells has a name, and knowing their name and how they interact will be important as we move forward. The convection cells that are closest to the equator are called the Hadley cells, so each of them has the same name. The next ones up between 30 and 60 degrees will be the Ferrel cells, and then the ones that are closest to the poles are aptly named the polar cells. One thing you'll notice is that there's a pattern of naming them. They are identical or symmetrical from one side of the equator to the other. Now, as a reminder, these are 3D, which means the Hadley cells from the left side will connect to the Hadley cells on the right side, similar to creating like a donut or a ring that goes around the planet Earth. So now one of the things we can do is we can start to examine what happens at the surface. As a result of these convection currents, you're going to have different sort of pressure belts that seem to form across different areas across the globe. Now, anywhere where you have rising air from your convection current, you're going to have lower pressure. So across the equator, where that air is rising, there will be a belt of low pressures. Along these 60 degrees north and south, you will also see similar patterns of low pressure because in those locations, you have air that is rising. Where you have sinking air, you will have areas of high pressure, which will form at about 30 degrees north, 30 degrees south, and the North and South Pole. Again, these pressure centers at the surface are only caused by the rising and sinking air from the convection currents that happen around the globe. Next, we will look at how those surface winds are going to change across the planet Earth. Now, one thing you have to remember is that air always moves from high to low pressure. So wherever there's an H and an L on the diagram, you can start to draw a mental image of where that air is going to go. So we're going to start at the 30-degree north line heading towards the equator, and you'll see right away that that arrow is not moving in a straight line. Instead, it is directed to the right because of the Coriolis effect. Now, it may appear that that arrow is pointed actually to the left, but if you were standing on that H and looking down at the L, it actually is pointed to the right. Now, this pattern will repeat over the entire belt of high and low pressure in that area. Now, as we look from the H, or the high pressure at 30 degrees north, to the low pressure at 60 degrees north, we will see the same thing. That wind is deflected to the right because it is in the northern hemisphere, and as it's moving, the planet Earth is rotating underneath it. That is basically the Coriolis effect. And then down from the North Pole, again, it's going from high to low, and you see a right-hand curvature or deflection of that wind. These represent the basic wind belts across the northern hemisphere. Now, something similar will set up across the southern hemisphere. The only difference is that the wind is going to be deflected to the left because you're on the southern hemisphere, and that's the direction the Coriolis effect will have on those winds. So now I can continue to simply draw in my wind pattern, and as we go, this becomes a little bit easier to do. And I see that it is almost symmetrical again across the equator. The only difference is the direction of those arrows is different because of the Coriolis effect. So lastly, each one of these wind belts will have a designated name. So remembering and being able to use these names is again important when we look at different weather and climate across the planet. Everything that is between 30 degrees and the equator will be the tropical easterlies. Now remember, we describe winds from the direction they are coming from, and these winds are coming from the east, so that is why they are called easterlies. They're called tropical because they're near the equator. Above that would be the prevailing westerlies. From 30 degrees north to 60 degrees north, the wind generally blows from west to east, which makes it a westerly direction. Now, this may not be hard to picture for students because if you look at most of our storm systems that you see on the radar, they are actually coming from the west because St. Cloud is in the prevailing westerlies. Up near the North Pole, you have the polar easterlies because those winds are coming from the east and are north and are near the pole. Now, to make this convenient, the names on the southern hemispheres are again identical. Because they're going in the same direction and are at about the same latitudes just on the southern hemisphere, it's easy to name them the same names. So remembering the pattern of highs and lows, the arrows and their directions, and the names of these wind belts is the main concept of this section. So let's take a minute and let's recap all of this information together. This diagram shows the combination of the convection cells, high and low pressure belts, the wind belts, and the wind belt names. Now, as a reminder, this all begins because Earth is heated unevenly, and this causes several convection cells to form all over the globe. Now, the pattern of the convection cells is relatively easy to remember, and it also is important to remember that these are three-dimensional belts, which means they sort of form little donut-shaped rings around the planet Earth. Now, as a result of these, we will get patterns in the pressure centers across different latitudes on the planet Earth. So at the North and South Pole, you will have high pressure because that air is sinking. At the equator, you will have low pressure because that air is rising. And notice the pattern that it always goes starting from the top, high to low, high, low, high, low, high. You will find several different patterns as we go through all of this information together. Now, these pressure belts also control the way that the surface winds will move across the planet Earth. Now, recall that these winds normally would go in a straight line from high to low, just like we've said several times in class. But since the Earth is rotating, they are then bent in a certain direction depending on which hemisphere you are in, north or south. Now, the last thing to remember is that each of these belts has a name. They are named after which direction those winds are coming from, so any of them that have an easterly name are winds that are coming from the east. Ones that have a westerly name are ones that are coming from the west. One way to help visualize the wind belts that we were showing earlier in the screencast is to look at a live example of them. This simulation shows the direction of wind on the planet Earth. Now, what makes it interesting is that this is a live look, the current conditions, and it's updated every hour. Right away, you'll maybe notice some patterns in the way the wind is flowing. Towards the equator, you will notice that the wind is flowing from the east to the west, which would make sense because we labeled those as the tropical easterlies. Now, as you move north and south from that location, you'll notice the prevailing westerlies, which are much stronger over the United States. One thing to help us visualize this is to scroll down to the South Pole, where we can see the prevailing westerlies making their complete loop. You also can find in the center of the South Pole some remnants of the polar easterlies that happen. This again is just trying to show us that the wind belts that we were learning about do in fact exist on the planet Earth, although they are maybe not as neat and perfect as we drew them on the diagram. I have a link to that simulation in Schoology if you wanted to play around with it on your iPad. This has been the screencast that goes through the formation and patterns for all of the convection cells, pressure belts, and wind belts on the planet Earth. This is a complicated topic, and I know that it can be a lot to take in all at once. Please feel free to let me know if you have any questions, and I will do my best to help you. Thank you for watching this long screencast.